let me just take a moment to send an email to the class. Make sure they're able to find us. I don't know. Is it lagging? It was just telling me not buffering on my end. Well, all right. Well, let me do this. Is it better now? Should be. Yep. I was trying to send an email to everyone, but I mean, let's forget that. If it's working, we'll count our blessings and move on from there. All right. Let's do this question that somebody had asked earlier. And, I mean, this will give us an idea. It shouldn't be blurry. It looks good from my end. Try uploading again. Is it blurry for everyone? All right. So again, the idea, first of all, is that you have the square root of a sum. And as you know, the square root of a sum is not the sum of the square roots. And by doing a tangent substitution, this allows you to get rid of the sum. So let x be a tangent theta, then dx is a secant squared theta d theta. And what happens? The dx becomes a secant squared d theta. This, the square root, becomes a squared tangent squared plus a squared. If you factor out an a squared, you get a tangent squared plus 1. And tangent squared plus 1 is secant squared. Square root of which is a secant. These disappear, and you're left with the integral of secant, which you know to be ln of secant plus 10. So originally here, let's do a triangle. You had tangent as x over a. Tangent, you know to be opposite over adjacent, so this is x over a. And Pythagorean theorem, why not a squared on top? Well, I mean, when you differentiate this, the a is just a constant. So tangent, which is opposite over adjacent, x over a. Pythagorean theorem, work it out on paper if you don't see it immediately. But this turns out to be a squared plus x squared. Exactly what you started out with. So secant, which is hypotenuse over adjacent, tangent, which is x over a, plus the arbitrary constant. And I now see, it is a bit laggy, right? And I now see what the issue was, because the answer in the book is going to give you this. And then you're thinking to yourself, well, my answer is wrong. I've got an A. I've got fractions there. What happened? Nothing wrong. Nothing wrong here. Somebody want to address how you go from the second to last line to the last one? Anybody? How do we go from here to there? Exactly, right? Here, this is actually ln of this plus this minus ln A, right? I mean, if you have everything over a common denominator there. So it's ln of this minus ln of that. And ln of A is just a constant. So it gets absorbed into the plus C. Exactly that. Well, it doesn't become an exponent, but it gets absorbed into the plus C. Exactly. Yep. There it is. How are we doing here? Questions? Anyone? We're good? Moving on? In the midterm, you can leave it. I mean, it's not, I would have accepted this as the answer. That would have been fine. Well, with the Pythagorean theorem, we were finding the missing side, right? We had a right angle triangle. This was A, this was X. So we found the missing side using the Pythagorean theorem. Today, our goal is to tackle integrals like this. Sophia is asking for the antigrade of secant theta. We've already done it at least twice in this course, and I suggested several times that it's an integral you should remember by heart because it comes up so often. The integral of secant is ln of secant plus tan. We showed that by multiplying by 1, right? If you multiply by secant plus tangent over itself, you multiply by 1, you're not changing anything, and you'll see that the numerator, when you multiply the secant in, is actually the derivative of the denominator. Still a bit laggy, isn't it? I don't know what's going on. All right. So our goal is everybody still there? I feel I may have lost some people. It's fine, thanks. All right, so our goal on the midterm, unless it's asking you specifically to find the integral of secant, you can just assume it. So this is our goal, or in particular, or in general, the integral of rational functions. One polynomial divided by another. It is a bit laggy on my end. It's probably my internet connection. Something's, yeah. Because I can see it. So our goal today is the integral of rational functions, one polynomial divided by another. Now, if you did 139, last semester, we completely reviewed polynomials. But for those of you who may not have done 139, let's take a few minutes to introduce some definitions and make sure that everybody is up to speed. First question that arises, what do I even mean by a polynomial? What is a polynomial? So polynomial is a function of the form an x to the n, an minus 1, x to the n minus 1, and so on, all the way down to a0, where n is a whole number and the AIs are real numbers. This is what a polynomial looks like. Let's take a few examples. Example. Three x squared minus x. Right, this is a polynomial. You've seen these before. You're very familiar with them. This is another polynomial, right? So the important thing is whole powers of x multiplied by real numbers. This thing is not a polynomial, right? Because square root of x, or x to the 1/2, is a fractional power. We don't want that. We want whole powers here. So no fractional powers. Let's continue on. And define the degree of a polynomial. Denoted degree of p is the largest power of p the largest power of x present in the polynomial. Take an example here. We had p as 3x squared minus x. The degree of p here, largest power of x, largest is 2, the degree is 2. Also known as a quadratic polynomial. Right, again, with q, the degree of q, largest power of x, degree is q, the degree is 3, known as a cubic polynomial. Right, so degree 2 polynomials are quadratic, degree 3 are cubic, degree 4 are quartic, and so on and so on. Definition. Given a polynomial, p of x, x equals a is said to be a root of p if p of a is equal to 0. So a root or a 0, sometimes referred to as a 0, of the polynomial. Questions here? Yeah, again, if you did 139, you saw all of that. But if you did 140, maybe it was assumed knowledge. Questions at this point? Anybody? No, we're good? Well, I mean, I don't know what you mean here. What I'm going to say is you need to show all your work. On an exam, you should show all your work. And that not only goes for Math 140 or Math 141, but really for all math courses. There's no need to explain secant or e to the x or cosine x. These known integrals are fine. But tangent, I wouldn't call it a known integral. Although if you look in the back of the book, it probably gives it to you. Instead, a simple u substitution does the trick. I would like to see that. There's no need to say, I'm going to do this technique or that technique. It should be clear to the reader if you're showing all your work. I do not expect you to use reduction formulas. In fact, I don't want you to use reduction formulas. Instead, if a question with regards to reduction formulas comes up, it's going to be prove this reduction formula. All right, let's take a few examples here. P of x is x squared plus 2x plus 1. I claim that x equals minus 1 is a root, x equals minus 1 is a root because if you plug minus 1 in, right, in for x, if you plug minus 1 in, this is 1 minus 2 plus 1, the whole thing is 0. I'll be writing the midterm for better or for worse, right? Consider this function, right? I'm sure that you recognize that x equals minus 3 is a root. And so is minus 4. Right? Minus 3 because 9 plus 12 is 21. Minus 21 is 0. And same with, yeah, I did write the final last semester. I made it easy because I thought you needed a break. But you can expect the midterm to be well, to be what it is. I mean, you should expect, yes, let's say this, it's going to be a lot of letters. A lot of letters because, look, I mean, if you take an integral, even a difficult one, well, I mean, I wouldn't call this difficult, but I mean, you know, we just did this. You plug that into Wolfram Alpha, it's going to give you the answer. So I'm not testing you on your knowledge of Wolfram Alpha. I'm testing you on your ability to solve integrals. And Wolfram Alpha has difficulty dealing with a separate, with another constant, right? I mean, this integral is not any harder than this one. They're of equal difficulty. If you can do one, you can do the other, and so on. Questions? Now, let me point out here, right, and I'm sure you've recognized this actually factors as x plus 1 squared. This actually factors as x plus 3, x plus 4, right? And I'm sure that that's what you did if you were looking for the roots. Right, so -3 is a root and -4 is a root as well. This idea generalizes not definition, but rather theorem. Theorem. If x equals a is a root of the polynomial p, then x minus a is a factor. What does that mean? In other words, p of x is equal to x minus a times q of x, where q is a polynomial of degree one less than p. I don't know how many questions I haven't even started. No, I've actually started thinking. I have 2 questions so far. So it'll be at least 2 questions. Probably around 15. It's very laggy. I don't know what's going on. All right. The question that arises naturally, well, you say that. You say I can keep it at 2. But 1 year, I gave a bunch of multiple choice questions and then 1 integral. 1 integral. This integral. And people were freaking out. It's not fair, it's this, it's that. So, I mean. All right. Well, we might not solve it per se, but you'll know how to solve it, for sure. The question that arises, no square root, no. The question that arises, how do we find Q? And the answer is long division. So, again, we did long division in 139, but if you were in 140, you might not have seen it. You probably saw it in high school, but if you didn't, let's do it now. Long division of polynomials is exactly the same thing as long division of real numbers. If you take a number, 935, and you want to divide by 5, right, the long division, you ask the question, how many times does 5 go into 9? Well, it goes in once. And then you subtract. 9 minus 5 is 4. Bring down the 3. How many times does 5 go into 43? It goes in 8 times. You get a 40 and you subtract. 43 minus 40 is 3. Bring down the 5. How many times does 5 go into 35? That is 7. And you are left with a remainder of 0 as expected. In other words, 935 over 5 is 187. Or 935 is 5 times 187. We're going to do the same with long division. Let's take an example. If you take a polynomial, x cubed plus x minus 2, it's easy. Synthetic, well, I mean, synthetic division is the same thing. So, I mean, if you're comfortable with synthetic division, that's fine. And observe, so back to this, observe that x equals 1 is a root, right? That's clear to see. 1 plus 1 is 2, minus 2 is 0. So x equals 1 is a root. So by the previous theorem, x minus 1 should be a factor. So let's do some long division. Right, when we want to factor this, so x minus 1 into x cubed. Notice that there's no x squared. I'm going to put a placeholder. I'm going to say 0x squared plus x minus 2. And we ask the question, how many times does x go into x cubed? Or what must I multiply x by to get x cubed? And of course the answer is x squared. X squared times x is x cubed. X squared times minus 1 is minus x squared. And we do exactly what we did before. We would subtract. This minus this is 0. This minus negative is x squared. I'm not sure how synthetic division would be easier if the roots weren't obvious, because you really need the root here to do long division, and synthetic division is exactly the same. And it doesn't matter if you never learned synthetic division. I never learned it either. This is the way to go. Again, if you are comfortable with synthetic division, we'll allow it, but there it is. And we repeat, what must we multiply to x to get an x squared? The answer is x. X times x is x squared. X times negative 1. And we subtract again. This minus this is 0. This minus this is 2x. Bring down the minus 2 and repeat. What must we multiply to x to get a 2x? The answer is a plus 2. And we subtract, getting 0 as expected. What are we saying? This factors as x minus 1 times x squared plus x plus 2. Of course you can check. Is it non-negative x squared up there? Maybe it is. Let's check. We can check. Right? I mean, by expanding this, if we multiply everything out, we should get this. Let's do it. This times this. So x cubed plus x squared plus 2x. And then minus x squared minus x minus 2. The x squares cancel out. And we are left with x cubed. 2x minus x is a plus x, and a minus 2. Exactly what we had. So we know it's right. How did we get x minus 1? We noticed that 1 was a root just by inspection, just by looking, trial and error, absolutely. Why did the minus 2 disappear in the middle? Not sure what minus 2 you're talking about. Are you talking about this minus 2? It didn't disappear. We just didn't bring it down quite yet. We reserved it until the end. So is fine. Very well. Let's try another one. Well, that's the thing with mathematics, right? The more you do, everything else becomes so easy. So, you were having trouble learning this in the beginning, but now it's trivial. And that's the thing, the more you do, everything else. 2 is a root. Thank you, Kenza. Kenza has observed that x equals 2 is a root, right? Because 2 cubed is 8. 8 minus 8 is 0. Very nice. So by the theorem I've erased, x minus 2 should be a factor. So let's do some long division. We'll do it over here. So x minus 2 into x cubed minus 8. And again, there's no x squared and there's no x. So let's put some placeholders here. 0x squared, 0x minus 8. And we ask the question, well, I mean, if you propose a root and you plug it in and you get 0, that's all the proof you need, right? I've never said that, just inspecting, but just looking all the time, though. So what must we multiply x to get an x cubed? And of course the answer is an x squared. And we subtract. This minus this is 0. This minus this is a positive 2x squared. Let's bring down the next term and repeat. What must we multiply to x to get a 2x squared? The answer is 2x. And we get 2x squared minus 4x. Subtract. This minus this is 0. This minus this is a positive 4x. Bring down the last term and repeat. What must we multiply to x to get a 4x? The answer is 4. And we get a remainder of 0 as expected. If the remainder is not 0, we've made a terrible mistake, either in the work or the fact that we didn't have a root to begin with. Sophia is asking, what about long division for polynomials without roots? And it's a valid question, absolutely. It works exactly the same way. Matt is suggesting to use this difference of cubes formula, but that's the thing, right? I mean, I don't know that formula, and I don't need to know that formula. It takes 10 seconds to work it out. And that's the problem with mathematics, right? I mean, if you're trying to learn mathematics by learning formulas, it's terrible. It's terrible. It's terrible. You're going to cram for it. You're going to cram that knowledge in for the midterm and for the final. You'll be frustrated, and once the final is over, you're not going to remember that formula ever. And there's no need to learn that formula. Long division gives it to you immediately. Sophia was asking, about polynomials that don't have any roots. And let's talk about this polynomial here. Does this polynomial have any roots? And you try by inspection. If you plug in 0, you get a 4. If you plug in 1, you get 7. I mean, that's not working. -1, you get, what do you get? You get 3, and -2, you get 4, and so on. I mean, nothing's working out. And you're starting to think, well, maybe there aren't any roots. But this is a polynomial of degree 2, or a quadratic polynomial. What can you do to find the roots? To find the roots, as Michael suggests, you can use a quadratic formula. So let's recall, if ax squared plus bx plus c is equal to 0, then x is -b plus or minus square root of b squared minus 4ac over 2a. Now, I just said you never have to remember formulas. Well, maybe you need to remember that one. You can always work it out, right? It's just a nice application of completing the square. But first of all, I'm going to assume everybody knows this formula. And if you want, take some time and work it out by completing the square. So here, if we're looking for the roots, -b plus or minus square root of b squared minus 4ac over 2a, and you see the issue, right? You see the issue, namely that the discriminant here is negative. And you know that you cannot take the square root of a negative number, so we're in trouble. There are no real roots. This polynomial has no real roots. Definition. Exactly, Sophia, as Sophia suggests. If the discriminant is negative, this means that the roots must be imaginary. Absolutely. We're not going to consider this. The no real roots is sufficient as far as we're concerned. Definition. A polynomial. Polynomial is said to be irreducible. If it does not factor into polynomials of lesser degree. Right? JD is asking if you'd be penalized for not showing your trials when finding a root. Well, I mean, if you have a root and you show that it's a root by plugging in, that's sufficient. If you try a few roots and you're not finding anything, and then you want to somehow conclude that there are no roots, that's not going to be sufficient. You really want to show that there are no real roots, either by using quadratic formula or something to that effect. Right, so a polynomial is said to be irreducible if it does not factor into a product of polynomials of lesser degree. Let's take an example. Consider the polynomial 3x minus 2. What is the degree of this polynomial? You know the degree is 1. What is the only whole number less than 1? The only whole number less than 1 is 0. And what are polynomials of degree 0? Polynomials of degree 0 right? If your largest power of x is x to the 0, then really you just have real numbers. So polynomials of degree 0 are real numbers. And if you multiply two polynomials of degree 0 together, or if you multiply two real numbers together, you're not going to get a polynomial of degree 1. So this polynomial, and in fact all polynomials of degree 1, are irreducible. Right? Because if you take any polynomial of degree less than 1, these are all degree 0, these are real numbers, and if you multiply two real numbers together, you're not going to get a polynomial of degree 1. You're just going to get another real number. So polynomials of degree 1 are all irreducible. Notice the example we just did. What was it? X squared plus 2x plus 4. This is a polynomial of degree 2. So there is hope that it factors into a product of polynomials of degree 1. But if it did, then minus a and minus b would have been roots. But you know that this polynomial has no real roots. So it cannot factor as a product of polynomials of lesser degree. So this polynomial must be irreducible as well. And wouldn't you know it, these are the only irreducible polynomials. Say, somewhat unexpected result, a priori, right? Theorem. The only irreducible polynomials are polynomials of degree 1 or polynomials of degree 2 with no real roots. These are the only types of irreducible polynomial. How are we doing here? Questions? Can't all even degree polynomials have no real roots? Indeed, as Michael suggests, you might have an even degree polynomial with no real roots, but if the degree is higher than 2, it has to be reducible. How do we know that? It's a valid question. How do we know that? And to prove this, you need to, I don't know that you need to, but an easy proof of that is to actually move to the realm of complex numbers. So that's very interesting. By moving to a more complicated setting, the proof is very easy. And the proof is that if you have in fact, the proof is that roots come in pairs. A number and its complex conjugate. And when you say x minus a number times x minus its complex conjugate, what you have is a real polynomial. So what do we mean by no real roots? Well, I mean, here we've proven that you cannot take the square root of a negative number. That's not a real number. And there it is. Those are the only 2 types of irreducible polynomials. How? I'm not sure what your question is there. All I'm saying is the only 2 types of irreducible polynomials are polynomials of degree 1 or polynomials of degree 2 with no real roots. Let's take an example. Consider this. Here's my question to you. Is this irreducible? Immediately, the answer is no. That's immediate, because the only irreducible polynomials are degree 1 or degree 2 with no real roots. This has degree 3. Cannot be irreducible. So it cannot be irreducible. In fact, it's easy to see that x equals 1 is a root, right? right? 1 minus 2 is minus 1, plus 1 is 0. So x minus 1 must be a factor. Let's do some long division. Didn't we prove x cubed minus 8 was irreducible earlier? I want to say we did not. Somebody pointed out that 2 was a root, so x minus 2 was a factor, and we did the long division, right? The x cubed minus 8, I believe we factored as x minus 2 times x squared plus 2x plus 4. Right, so it reduces. It reduces as a product of lesser degree polynomials. This is a polynomial of degree 1, so it's irreducible. And this was a polynomial of degree 2 with no real roots. So that was irreducible as well. Somehow my chat has been disconnected. Are people still hearing me, or are we still having connectivity issues? Oh, I think we're back. How do we reduce higher even degree polynomials without real roots? And Jennifer asked a question earlier. We'll discuss it momentarily, but first let's do this. Let's decompose this into a product of irreducible polynomials. Thank you, everyone. Right? X minus 1 must be a factor, so let's do some long division. X minus 1 into x cubed plus 0x squared minus 2x plus 1. And we ask the question, what must we multiply to x to get an x cubed? The answer is x squared. This minus this is 0. This minus that is x squared. Bring down the next term and repeat. What must we multiply to x to get an x squared? The answer is x. And we subtract. This minus this is 0. This minus this is a minus x. And we ask the question, what must we multiply to x to get a negative x? The answer is negative 1. And we get a minus x plus 1, getting us a remainder of 0. So it's easy to see that this factors as x minus 1, x squared plus x minus 1. This is a polynomial of degree 1. So it's irreducible. This is a polynomial of degree 2. So it may or may not reduce, depending on what the roots are. If we look, so this is irreducible. And what about this? X squared plus x minus 1. If we look for the roots, using the quadratic formula, b squared, negative b plus or minus square root of b squared minus 4ac all over 2a. That actually factors. This is not irreducible. This factors. Right, so x cubed minus 2x plus 1, which we had factored as x minus 1, x squared plus x minus 1. This is irreducible. But this factors again, and we have the two roots there. X minus 1 root times x minus the second. What if we find a root using the quadratic formula for polynomial degree 2? Is it irreducible? The answer is no. We have it right there. We have an example right here. How are we doing? Now, Jennifer asked a very interesting question earlier. X to the 4 plus 1. Now, what about x to the 4 plus 1? My question to you is this irreducible? Is this irreducible? The answer is no. This is a polynomial of degree 4, so it cannot be irreducible. The only irreducible polynomials are polynomials of degree 1 or polynomials of degree 2 with no real roots. This is a polynomial of degree 4. It has to reduce. It has to factor as a product of polynomials of lesser degree. The come in pairs business was referring to complex numbers. Here, x equals -1 is a root, and so is the conjugate of -1, which is -1. So it kind of breaks down when you have real numbers themselves. But if you have complex roots with an imaginary part, then they do come in pairs, right? If a plus ib is a root, then a minus ib will also be a root. We're not going to discuss complex numbers, so it's not a big deal, but that's what the come in pairs was referring to. So back to this, x to the 4 plus 1 does factor. It's not clear exactly how it does, so let me give you the answer. So that you can work it out just for fun. But there it is. We knew that it was not irreducible because it was a polynomial of degree 4. I claim that it factors as this. You can verify that by doing the product, right? Just work out the product here. Expand everything, you'll see that you get x to the 4 plus 1. And I will let you check that these polynomials are irreducible. But there it is. Well, now I know what you're thinking. All we did was review polynomials. Where are we going with this? Yeah. It's a valid question. How did we find that? Again, you don't need to know how to find it. The technique is, again, using complex numbers. So let's not worry about it. The only thing we need to worry about is the fact that this was a polynomial degree 4. So immediately we knew that it was not irreducible. That's all that's important here. I mean, it's a very nice result, but a bit beyond this. Where are we going? Our goal is partial fraction decomposition. And let me state it, because we haven't done anything new today. You could do that, absolutely, right? You could assume that it factors as polynomials of degree 2. So x squared plus bx plus c times x squared plus, I don't know why I started with b, dx plus e. Multiply everything out and equate the coefficients. You could do that, absolutely, very nice. And solve for b, c, d, and e. Partial fraction decomposition, what does that say? Let p over I started it out wrong. Let p and q be polynomials. Be polynomials where the degree of p is strictly less than the degree of q. Suppose further that q factors as a product of irreducible polynomials, q1 to the k1, q2 to the k2, qn to the kn, where the qi are irreducible polynomials. Then there exist polynomials, Pij, where p of x over q of x is equal to p11 over q1 plus p12 over q1 squared all the way to p1 k1 over q1 k1, p21 over q2 over q2, p22 over q2 squared, p2 k2 over q2 k2, all the way to pn1 over qn and pnkn over qn to the kn. There's this polynomial where in fact, I should say there exist, let me throw in a unique here. There exist unique polynomials, Pij, where the degree of Pij is less than the degree of Qi. No, this is all midterm material and more. Why do some have squares and some not? Let us explain all of that by taking a few examples. Yeah. It's difficult to wrap your head around all of this nonsense, but let's take an example. Hopefully that'll clear everything up. Should we perhaps call it a day and we'll pick this up again next time? It is 11:30. Do we want to take a minute to take an example, or well, let's take a minute so that we have an idea of where we're headed. Let's take an easy example. Yeah. Let's just do one quick example. 1 minute. 1 minute. So if everybody stops asking questions, we'll end in a minute. Decompose the denominator into, well, hopefully this will be cleared up with this example. Decompose the denominator into a product of irreducible polynomials. The denominator is a polynomial degree 4. So you know it's not irreducible. Let's factor it. You can factor out an x squared. So this x squared plus 1 is irreducible. You can check the discriminant if you want. You can verify that there are no real roots. So this is irreducible. And this x squared can be viewed as x all squared, where x is a polynomial degree 1, so it's irreducible. So this is irreducible. And this is irreducible. Everybody with us? And the numerator is a polynomial of degree less than the denominator, right? P over Q, the degree of the numerator is less than the degree of the denominator. So partial fraction decomposition, x has a root of 0, that's correct, but it is a polynomial degree 1. And that theorem says that the only irreducible polynomials are polynomials of degree 1 or polynomials of degree 2 with no real roots. So polynomial degree 1 is irreducible. Partial fraction decomposition, this whole mess here, what does that say? It says, well, Q has been factored as a product of irreducible polynomials, right? So your Q1 is x, your K1 is 2, your Q2 is x squared plus 1, and your K2 is 1, and that's where it ends. That's all you have. So partial fraction decomposition says that this decomposes. Look at your first irreducible polynomial. It's a polynomial of degree 1. So we search for a polynomial of degree 0, 1 less, on top. And then you continue until you've exhausted the power. So a over x, b over x squared, and you would have continued in this fashion until you've exhausted the power. Well, you've exhausted it at 2. So that's it. Now you move on to the next irreducible. The next irreducible is an irreducible polynomial of degree 2. So you search for a polynomial of degree 1 on top. Cx plus d. This is how all polynomials of degree 1 look like. Over x squared plus 1. And you continue until you've exhausted the power. But this was power 1, it's already exhausted. You would have moved on to the next irreducible, but you're done. There it is. So now you solve for a, b, c, d by bringing everything back over a common denominator. So here I'm missing an x and an x squared plus 1. Here I'm missing an x squared plus 1. And here I'm missing an x squared. And now, since the denominators are equal, you can equate the numerators and you can solve for a, b, c, and d. The point being that whatever a, b, c, and d are, this is going to be easy to integrate versus this, which would be very difficult. There it is. So it's a lot of algebra instead of difficult integration. We'll pick this up again on Thursday, and we'll take it from there. Hopefully, the internet connection will be better. This partial fraction decomposition comes from long division. Not so much, right? I mean, how do you know that you can break it up this way? Again, the proof of that comes from complex numbers. We'll do it again on Thursday, no problem. Right, the idea is you decompose your polynomial into a product of irreducible polynomials. So x, and you have 2 of these, times x squared plus 1. Both of these are irreducible polynomials. And then you look for a polynomial of degree 1 less, right? Because you want the degree of this has to be strictly less than the degree of the irreducible. So irreducible degree 1, so 1 less is degree 0. Irreducible degree 1, but you have 2 of them, so 1 less, and so on, until you've exhausted, and then you move on to the next, and you repeat. We'll do this again on Thursday, and then we'll see some examples. In the meantime, maybe practice long division and all the other techniques, integration by parts, trig sub, because what's going to happen here, right? I mean, you're going to decompose according to partial fraction decomposition, but then you still have these integrals that you're going to have to evaluate. And you're going to have to evaluate them via all the techniques that we saw previously. Thank you all for coming, folks. I will see you on Thursday.